Next up for physics then is topic D, light and lasers. Now, I just want to very early on make this point that lasers is spelt with an S because it stands for light amplification by the stimulated emission of radiation. It is an acronym, so you cannot replace it with a Z even if you're American. It is an S in the middle. So please, 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 please don't make me grumpy and spell it right. Okay, moving on from my little rant. This topic is mostly about how light is used for communication. And we start really, really basic, and we start with Morse Code. It's a really simple example of how light can be used to send signals and to send complex signals over long distances. So it's simply a case of using lights where you turn it on and off, and you either have a long on or a short on, so dots or dashes, and that is how you send your signal, and you can send complex coded information. Now this is a really nice example because it's an example of a digital code, because when we're sending information, all we're sending is on or off. So the light is either shining or it isn't. So that makes it digital. It only has those two settings. There's nothing in between. It's all or nothing. And that's what we mean when we're talking about digital signals. So we're starting with Morse code as our first example, but we get pretty more sophisticated much faster, and we jump from Morse code to fibre optic cables. Fibre optic cables are just light signals. It is literally just flashing light on and off. It just happens to go along the fibre optic cable. And they're normally plastic, and all that happens is the light reflects inside the cable to travel from one end to the other. So there's my light signal going along the cable. Now, the only thing we have to be careful of with these is that you have to make sure that the light hits at the correct angle so that it always gets reflected. Because if it hits at the wrong angle, it could get refracted and actually leave the cable instead of getting reflected and staying inside. So we'd get signal loss. Now, you will always get a little bit of signal loss, but as long as most of the information gets through, you're fine. Particularly because we send digital signals and all I need is on or off. I don't mind if it looks like a slightly smaller on, I still know it's got to be on. It doesn't matter where it is on, how high or low the peak is. So what we're looking for is it to be reflected inside the wire. So, as I said, to make sure it gets reflected, we've got to make sure we get it within this magic angle, and it's called the critical angle. And we need to make sure that we hit at an angle that is larger than the critical angle. If we're smaller than the critical angle, we get refraction. If we're bang on the critical angle, the light will travel along the edge of the surface. And if we're bigger than the critical angle, we get total internal reflection, TIR. And that is what we're looking for. So just to give you some examples here, these are supposed to be semicircle blocks of glass, and again I've got my normal on as before, so my light ray goes in, and this one's just been refracted, and you can tell that because it's changed the angle and it's left the glass block. So that one's been refracted. Right, this one here, we've gone for a slightly bigger angle, it's come out the other side, it's still been refracted, so I haven't quite made it to the critical angle yet. So this time I go for a slightly bigger angle, and my light ray travels exactly along the edge of my surface. So it's been refracted, but it's only just barely refracted. If I go slightly bigger, I then get reflection. So that means that I am more than the critical angle. So that's how we make sure it happens, and this is how it changes. So we just want to make sure that as our light travels down our fibre optic cable, it is always hitting at larger than the critical angle. So we get the maximum signal sent down. So there's our critical angle. Some uses of fibre optics, they really like endoscopy. So basically where you put a tube down someone and you can have a look at their insides. So that's a good example. And then obviously telephone and internet cables also use fibre optics. Don't give the example of, like, I know you get fibre optic Christmas trees, but they are fibre optics, but they're not for communication. They are for decoration. So just watch that one, because I know sometimes that's the first thing that pops to your head, but we're looking for communication uses. And I know endoscopy might seem like an odd way of saying it's communication, but it is, because we're getting information from one place to another, so it still counts. Okay, we mentioned lasers at the beginning, or I went off on one about how to spell them. Laser light is really special because white light, like the light that we get from the light bulbs or even from the sun, is a mixture of colours. It's got all the different colours and they're all in different phases. So the waves that come are all at different points in their cycle. They're not doing the same thing at the same time, they're just a jumble. Laser light is monochromatic, which means it is only one colour. So even if I had a red light, I would probably have 100 different types of red in there. Laser light would only be one shade of red. So it's kind of like going to the hardware store and buying a can of magenta. It is only magenta. It's ever so different to, I don't know, classic magenta. You know what it's like at paint shops. So it's just that one thing of red. And what's even better is that all the waves, all the information is doing all the same things at the same times. So every particle that's going up is going up at the same time. So it's not like one up, one down and all over the place. It's all what we call in phase, which just means that the light is really good for certain uses. It's a really strong type of light. It's got lots of energy and it's very easy to transfer that energy. And the use that you need to know about is that it is used in CD players. So just to try and show you how it works in CD players. Information on CDs is stored digitally. So remember I said a digital signal is something that has only ons and offs. Well, on the CD, on the surface of the CD, there are bumps and pits. So they represent the ons and offs. So if it goes up, it's an on. If it goes down, it's an off. And that's how it works. Then the laser light is shone on the CD and it reflects differently if it hits a pit or if it hits a bump. So like that. So there's my flat bits and my lumpy bits. And because then if it gets reflected back to the right place, it's on. If it doesn't, it's off. And that's how we get the information off the discs. So that is lights and lasers for you. Remember, if you've got any questions, don't forget to write them down so you can ask me when you see me.